you for your patience. Y tienen que arreglar. Okay, so now we will have our keynote speaker, Dr. Luis Felipe Zapata Rivera from Embry-Riddle University, Prescott campus.
Thank you, Dr. Petrie. And I hope everybody is awake at this time. We're all tired, I know. So I'm going to try to keep it short and try to cover as much as we can in around 35 minutes of presentation. So my presentation title is Online Laboratories as a Tool for Engineering Education. You have the clicker? Or our agenda will cover the following topics. We're going to give a context of IoT systems that most of you already got during our presentations before, and how IoT is used in the educational context. That's the second topic. Third, we're going to elaborate on how online laboratories are used in engineering context, the role of the artificial intelligence in this field, As you know, artificial intelligence has become a key topic on every aspect of society uh, at this point. And online laboratory providers are going to review some of the key players in this field. And at the end, I'm going to show some implementations and some photos of some labs that we have worked in the past. So let's start with a context in IoT systems. So IoT is Internet of Things, and that's more a commercial name, right? That was given to devices that are connected to internet. As we mentioned in our workshop, it's a name given to constrained devices in terms of memory and processing that are internet capable. Um, you can see examples in home automation, smart cities, industry, and examples are, for example, when you have a fleet of trucks that are transporting ice cream, and they need to be monitored with temperature sensors and regulating the temperature for during their trips. So those are technologies that incorporates IoT systems to monitor these devices, or for example, the camera, the security camera in your home that you can access through the cell phone and monitor the camera. That's also considered an IoT system. Uh, Smart watches are another example of IoT systems that they can count your steps and help you in monitoring your vitals and your heart rates and some other variables. Smart cars or autonomous vehicles, they also are equipped with sensors and actuators to accomplish automation on their autonomy in their um, operation, like Waymos in Phoenix or in San Francisco. These autonomous cars are applications of IoT systems. Some ideas that we developed for this presentation were advances in internet and hardware technologies have now put us here at this point where we can implement different solutions and being very efficient trying to accomplish applications. Um, these devices, the IoT devices, are everywhere right now in different contexts. So I already mentioned about that. Automation and entertainment is the main users of these technologies. And we saw an opportunity of application of these technologies in education. So the educational context, specifically the online laboratories, are um, contexts of application of IoT systems that are that I think everything is still to be done. So there is just a few implementations, not too much development in this area, but we are going little by little doing some improvements in the field of education. Just to put it into perspective, these are some numbers that I was researching and updated for this presentation this week. And it's about the market value of this industry of IoT. Um, for the year 2024, the market value of this technology was 1.39 trillion, or thousands of billions, and this is including all industry, educational, IoT applications, including automation of machines in industry, including cloud services of IoT. And main players here we're going to see later are companies such as Amazon or Microsoft or Google. So they invest a lot of money in these automation systems. The perspective of growth of these IoT systems and the amount of devices also, it's projected to grow at a pace of 11.4% per year from now to 2030. So it's a very good outlook for these type of technologies, right? Um, the market value for online education, it's $300 billion, and it's around fourth of the value of IoT. So I'm just putting these numbers. I'm going to explain later why I put these numbers together. So online education, including providers, online universities, platforms, LMSs or MOOCs platforms, all of these industry has a value of $300 billion for the year 2024. And later, I show the market value for online laboratory industry, including industrial applications and education applications for online laboratories, including simulation systems, hybrid systems, physical systems, and remote labs. And that's 3.8 billion. So that is like 10% of the online education value. One is 1/4, and the other one is 10% or 1/10 of the other. So we can see there that is a big opportunity on developing these systems from the perspective of creating a company in this field. You can imagine that you can impact those online education systems with your products, and you can be very profitable in that sense. Also, the outlook of growth is 12% per year from now to 2031 in this online laboratory system. I forgot to mention that in IoT systems, we have industrial, we have medical, we have transportation. So we have different fields involved in the IoT industry. Key players in the IoT market are companies like such as Amazon, Microsoft, Qualcomm that produce components for these systems, Intel, PTC, Cisco, Oracle, SAP, Siemens, General Electric, and many others. So these are just some of the key players in the industry of IoT. Below these companies, you have also IoT enablers or another companies that are more focused on providing IoT services to the end user. And those are companies such as Telit, an Italian company that offers cloud support for IoT systems. And they are based on Amazon Cloud, but they translate the business model in terms of kilobytes per second into transactions per second, or how many times a thing, it's called Internet of Things, so how many times a thing communicates to the server. So based on transactions. Also, it's important to note that there is also communication companies that offer 5G cellular network capabilities for IoT systems, and they also have models that charge per transaction and not per gigabytes. They charge per, you have 1 million transactions, 2 million transactions. And these companies are below the cellular providers. Online laboratories in engineering. So this is a very important topic for us and has been our research topic for the last 10 years now. We started in 2015 with Dr. Petrie here. She started even before that with some projects in online laboratories. So I joined her in 2015, and we made some progress on standardization, some progress on interfaces, and I think we were in a point where technology was going better and better, and we were able to do implementations that were more capable and more robust. What are the goals of online laboratories for us, or for our research? Was to improve accessibility, scalability, integration, interoperability, traceability, reliability, security, and privacy aspects. So we were concerned about all of those topics, and every implementation we were making, we were thinking on developing one of these characteristics. We also joined the standardization groups from IEEE to learn first and later to show more implementations. There is a context that was done by Javier Garcia Subia from University of Deusto in Bilbao, and in 2016, and he updated this in 2022. He ran a study over implementations of online laboratories around the world, different groups, different universities that were developing these technologies, and he found that very few of these implementations, he reviewed over 300 implementations, very few of them allowed durability and scalability, or that were robust solutions. And most of the evaluated systems were having problems of accessibility or access, like availability, accessibility for people that have any type of limitation or different type of characteristics to access the system. And he also found that many of the projects were not available at the time he was evaluating them. So a university started a project, and it was very common that some years after that project is canceled or closed because it was maybe money coming from a grant or an internal grant in the universities, and the professor did some implementation, and later they couldn't maintain the servers, or they couldn't pay for the cloud, or the hardware was failing and they didn't maintain it over a long term. So many projects were not working or had errors in the access. So he has a full report. You can refer to that paper, and that report is very interesting because it gives us the panorama of when we develop projects in universities that they don't translate directly to a startup or company. Many of these projects ended up being in a shelf or in a closet. So our motivation was to how we can enhance online education, or education in general, can be blended education or hybrid models of education, with offering hands-on experience or lab experience based on online laboratories, specifically for engineering programs. Blended learning programs, we also wanted to offer alternatives for hands-on experimentation for remote students that are not close to a physical lab, and how that can be managed. And also how to provide low-cost infrastructure. So one thing is to have a lab equipped and maintained, where you have to pay electricity bills, maintenance people, lab assistants, and all of that, and equipment gets old quickly in 5 or 10 years, and depreciation affects all of these equipment, and how we can create labs that are more sustainable, that we can maintain easily and with a low cost of production. In this case, we were also thinking in not just develop new labs, new online labs, but adapting current labs. So physical labs that already exist, what we have to do in that lab to attach a controller, attach a computer, and how we turn that physical lab into a remote or online lab accessible from the outside, from the internet. To support this work, we also collaborated and were part of the development of the 1876 IEEE standard that defines a multi-layer architecture that starts from the bottom layer of hardware and software libraries, and builds up into something called lab as a service. So every laboratory experiment will be offered as a set of services into the server, so the users can consume those services on demand, depending on what they need. To later build another layer that is more educational, that is called the learning objects, similar to what we do with SCORM in the past or with other standards for e-learning. We also propose in this standard ways to package, put in a package, implementation of a laboratory with all the configurations. And maybe you saw in our demo in the morning how we were generating scripts for the video streaming, scripts for the functions of the lab. And these are all the elements that you deploy into a system. So our goal is like to create a format, or was to create a format that contains all the elements of a lab that you can just deploy in a platform, web platform, and you get a functional laboratory. Imagine like the PDF, that PDF of labs, or the zip of files, of labs, so this type of notion. These learning objects are deployed in MOOC platforms, can be deployed in LMSs such as Moodle or Canvas or Blackboard, and we can use other standards to integrate them, like LTI. Maybe you're familiar with LTI, Learning Tools Interoperability, and we can make it compatible to the LMSs, Learning Management Systems. And two transversal layers that are the learning traces and outcomes that we also mentioned in the morning with the use of XAPI to keep track of what's going on with the interaction in these labs. And that's where AI will be useful here, because we are collecting tons of data from users' interactions with labs, and how this data becomes input data for AI models to later suggest to the students different activities or recommend different laboratory practices or laboratory experiments to perform. The other security pillar or layer, it's called, or transversal layer, is the authentication and authorization systems. And there is a lot to do still in that realm. So we can say that our online laboratory systems, if I can say hackers are not interested in to attack online laboratory systems, but if they were interested in to attack online laboratory systems, it's very easy to attack, because these are hardware systems combined with software systems, and there are many points of failure that they can exploit and they can take advantage of. So innovations to improve current implementation. So we thought we need to reduce the cost of implementation. That was key. Point number one for us was how we can use open source technologies, open access technologies, open source hardware and software to do our implementations. And I think we accomplished that in our project. How we add features to these labs of interaction and adaptability. And that was part of our main goal, was how can we make these labs more dynamic in terms of operation, administration, and deployment. So how users can really use it from different devices, cell phones, tablets, computers, how they can see the lab differently if they have some different characteristics. And that's the adaptability part. That can be supported by artificial intelligence also. And the application of standards is our third pillar for this implementation. It's how we define or support our implementation in an existing standard, so we can configure the labs with the same metadata fields, where the activity is named the same for every lab. It's correspond to the same field. When the activity, the evaluation also has some fields, so platforms can recognize those metadata titles or tags, and you can interoperate or transfer labs from one platform to the other. And that's what was developed in the IEEE standard also, all the metadata definition. This is a concept map based on Joseph Novak's theory of concept maps. Maybe you're familiar with it. This was developed in the IHMC, Institute of Human and Machine Cognition, the same group that developed concept maps for NASA and the Cancer Institute in Florida. And this group developed with Joseph Novak a theory of learning based on concept maps. I'm not going to, this is not the time for talk about that, but basically it's how to define how much a person knows about a topic, to evaluating how they can draft a concept map in the topic. So a kid can draw a very basic map of a specific topic. A high schooler might draw more details and add more elements into the concept map, and maybe a college student will have even more support, more core concepts, and the map will look more full of information. Like taking a photo of your brain and see how those connections work. There is cross cross relations, and so on. So there is a very beautiful work with NASA, and the work is called Why We Should Go Back to the Moon. And if you check those sets of maps online, it's all the justification on why we should back to the moon, the humans should go back to the moon, and what are those goals. NASA did it with experts and engineers, and that was a very important work because they apply something called knowledge elicitation. And knowledge elicitation is to interview an expert and extract a concept map. And when engineers retire from NASA, they leave these maps for the next engineers that came to the projects. So I just drafted there some aspects of the online laboratories. So I'm going to share this presentation with you, and you can read it more carefully. What is the role of artificial intelligence in this field? So we can optimize so many things with AI in these laboratories. One is how we can improve the scheduling, because sometimes we have labs that can only be used by one user at the same time. So you can use some smart scheduling to provide access to more students. Or you can automate data collection and collect data for auto calibration of equipment and collect data for analysis of results of the labs. You can personalize learning experiences with AI, and you can analyze the students' interactions and adjust difficulty level of experiments. That's part of the adaptability. If you have a robotic arm, and the robotic arm is accessed by a student in the first year of engineering, this robotic arm will offer, through the online interface, some basic controls and some basic activities for that student that is a new student in engineering. But if this same robotic arm is accessed by a student in the controls class, that is maybe a senior or junior level class, this robotic arm will be more configurable. Now the student can send control functions to it and tune specifically how the claw press the element that is grabbing with the claw. So different uses of the same laboratory station according to the user and the context of that user. We were also thinking on recently about programming language agnostic laboratories. So the student creates a code that needs to run in a laboratory station, and it doesn't matter the language he uses to program. The AI system can help translating that code into the code that is compatible with that specific system, and the student can accomplish a solution based on what they already know about programming. Another solution or proposal is to have a tutor, a virtual tutor, that guides the student on how to create the code for that specific lab. So those are uses of AI in terms of learning experience. Create individual learning paths, ensuring students with different skills levels can still benefit, is what we were talking about, the difficulty level of the labs, and how to propose a path of experiences that the student should follow to become an expert in the field. So the professor can be part in this process, but the system can suggest and recommend parts of that. Track learning styles, and this is important when you track things because the XAPI can collect messages or statements, and what we can do is identify how many times the student tried doing the lab, and maybe if he accomplished the solution by just testing so many times, but maybe without an instruction, or if the student try less amount of times, but they were more effective on getting the solution. So you can see that progression of the student across the interaction. Online laboratory providers, so these are some companies and universities. I couldn't put all of them. I just select some that I have collaborated with or that I know about. And these are in terms of companies. Labster, it's all virtual labs, so simulated labs, same as PHET, P-H-E-T. There are labs for physics, for chemistry, for simulations about different basic fields. We have Quanser. Quanser is a instrumentation equipment producer, and Quanser has also a section of online labs. Microsoft has a simulation, and you can see in Microsoft Robotics, and they have some simulations for embedded systems. Labsland, it's a company that was created from a project in University of Deusto in Bilbao, and we have collaborated with Pablo Orduña, that is the CEO of this company. He collaborates a lot in Latin America with universities in Costa Rica, Argentina, and some other countries, Colombia, and they take advantage of Labsland implementations. They implement remote labs and something called a, high concurrency labs. So they create labs where people can connect multiple users and use pre-recorded videos of the lab, and it's called concurrent. They create concurrency by recording the result of the experiment, and the user will feel that he's doing it live because it's the same result over and over. What else? We have Go Lab, Acron Robotics. We have Lab in a Window, that is the initiative with Dr. Petrie here at FAU. And about universities, we have in Mexico the ITESM, that is the Institute of Technology, the Studies and Technology of Monterrey. And this university is very big, and they have a very good implementation of remote labs. Professor Manuel Macias is the one that is leading that project. UNED in Spain, we have here Manuel and his group. They have developed online laboratories in UNED, and they also were part of the IEEE standard development. University of Deusto, that we already mentioned, with Javier Garcia Subia. Pro the Atlantic University, this university. TELUC, that is the virtual university of University of Quebec in Canada. Professor Hamadou Salih Hassan, he also is working there. And MIT started and closed that project of iLabs, and they were the pioneers of the initial implementations of online labs. But I think the project was closed in 2019. In Lab in a Window, here at FAU, in collaboration with Dr. Petrie and Laxey, we have developed a series of experiments and implementations. We define something called a Smart Adaptive Remote Laboratory. This is the general architecture, and we have the manager of resources with services around that manager. That includes the authorization services, galleries, composing elements for creating new labs, schedulers, security and logger mechanisms, session manager, and authentication. And these elements together with the smart components. The smart components, we're talking about the integration to standards that will allow to adapt versions of the labs based on data analysis. Learner data collection, so we can log information about that to perform learning analytics. So this is the architecture of this smart adaptive laboratory, and OLMS is Online Laboratory Management System. Some of the implementations, just to move forward, and this last part is just some implementations. This is in the top left, you see a equilibrium table where it's used for control systems. So you have a ball on top of the table, and the students need to create the control functions to keep the ball in equilibrium on top of the table, or to draw a pattern on the table. So the weight of the ball it's like a touch screen, the table, and if you mark with a marker on top of the table a pattern, the ball will follow. They have to develop a function that follows the ball the trace of the marker. So this is a control system, and it came originally with National Instruments technology, like the Elvis, and we adapt it to Raspberry Pis and control it with open source technology. This was a donation from Acrom Robotics to our project. In the bottom right, we have the what we call the ADB, or Actionable Data Book. That is basically an ebook that integrates access to remote labs. So when you're reading the ebook that is in format EPUB 3, that is an open source format for ebooks, you can include rich content of the ebook accessing the internet. So when you're passing the book pages, at some point, instead of having an image of an example in the book, you can have an animation or a control of a real hardware. You can connect reading the book to a real hardware. So that reminds me, like the photos in, have you seen the frames in the newspapers in Harry Potter? They move and they have videos in the newspapers. We wanted to give life to the books, right? And how they can interact with simulations and actual hardware inside the book, the pages of the book. This was presented in the Frankfurt Book Fair and was very successful. A company called, Dr. Peter remembers? The company, it's called Repub IT. And Repub IT with John Costa. And John Costa, we collaborated with him for 6 months or so, and we were able to attach that lab to the ebook. It was a very interesting experience. Here we have some of the work we did. Also, Perry Weinthal was involved in this project with Dr. Petrie, and I implemented a basketball game that is a multiplayer game where you have 2 users that can be located in different places, and they can throw balls to the game, and the game senses how many balls have passed through the hoops and count the points, and they can compete playing the game as a basic experiment, but they can also code, Python code, to change the behavior of the game. And that's a collaboration lab. So 2 users can connect to it and use it. It was implemented with a toy, a basketball toy, that the cost was around $5. There is a store in the United States called Five Below. It's a store where you can go and buy things that are $5 or less. That's where we got this basketball game. And in this image here, you can see that is a breadboard with a circuit connected, and that was the students need to implement a circuit and action the push buttons to throw the ball in the remote lab. So it's a combination. They have a hardware at home that they interact with, that generate signals that go to the computer, go to the cloud, and goes to the lab in the university and makes a behavior in the university. So we call it hybrid, because it has part remote, part local. And the Tektronix oscilloscope was a project with Mr. Perry Weinthal, and we were able to send digital signals through the platform, and those signals were plotted into the oscilloscope in the lab, and they could see it through the camera, and we generate a virtual control of the remote oscilloscope. So in that case, one oscilloscope can be accessed for multiple students, and that will maybe optimize the use of this device. Current activities, so we are collaborating with Dr. Petrie from a university that is Embry-Riddle and Florida Atlantic. So I meet regularly with her group, and we are making progress in the development of the labs. We are doing now auto-generated graphical user interfaces that adapt to the needs of the lab. We are doing automatic grading for the labs. So there are test cases where the student have to follow different steps, and the lab is auto-graded. So the professor will have this characteristic. I'm working in my university with aircrafts and drones, because my university is an aerospace and aviation university focus. So I have projects related to drone control and simulation of aircrafts. And These are more experiments that I'm going to show. This is a low-cost implementation of a railroad crossing system, and this is how the students see it in the web. So in the web, they have an augmentation of the environment with a train passing in the background, and the students can control, in that case, when to light up the semaphore lights, when to open and close the gate, and when to ring the bell. So there are 3 actions and 1 video of the train passing left to right or right to left. And that can do it, they can do it with code or with some other type of electronic circuits. The same basketball game, we control it with the same basketball game. We did it for different applications with blocks. For example, here we have a color generator that Harry presented in the morning with the workshop. And it generates different colors, and the color is generating in an LED combination of RGB, and there is a servo motor that changes the location of the arrow depending and points to the color that is generated with the LEDs. This lab, we also generated to use Blockly, that is a block-based programming language. And so that's why I was saying about agnostic, programming language agnostic, is because our labs can run code in Python, but can also run Blockly. And we wrote a compiler that translates from Python generated by Blockly into Raspberry Pi, GPIO, and libraries to control the system. Robotic arms, so we have open, close, moving up, down, left, right of the robotic arm, and grab balls. It's not visible in the camera for that one. We also generate some interfaces to generate logic design circuits or logic gates arrangements to generate some inputs to the lab. So the student has some software here that they can call directly from the lab, create a solution, and translate that solution into actions for the lab. And what we have in the left is the composer. This is an early version of the composer. This might have more than 5 years, but we have a new version of this composer. And it's where the professor defines this experiment is going to be named like this. It has this description. It has this activity to the students to perform. It has this metadata difficulty level, if reports or not to XAPI, publishing date, publishing time, duration of the activity in minutes. So you can populate those fields and have more control about the activities. About the self-grading, this is for Dr. Peter's class. So she asked us to develop a test case to evaluate the students' solutions. So they have their kits at home, their personal kits, they implement the solutions, and they run the inputs, and the output should be some specific, let's say a logic equation or a Boolean logic equation. And this Boolean logic, they have, according to the arrangement of variables, an output based on the inputs. So the students create the different inputs and click evaluate, and the system start passing through a series of tests and grade if they're getting the correct outputs in the circuit. But the circuit is at home with the student, and the validation is happening in the server, right? So this is an interesting way to auto-grade labs. This is the equilibrium table, but now accessed through the interface of the SAR system. We are almost done. This was one experiment during the pandemic. We used the API of Zoom API, to generate sessions with the students and share the control of the computer in the lab. So the students were at home, and they were controlling the computer in the lab, and the microcontroller was in the lab. So they could write code in the remote desktop application and see through the camera the behavior of the output. So I ran in the first semester of COVID. I put all my students to keep working in the lab from home through Zoom because I didn't have SAR ready for these labs. So I just used Zoom API to develop that. It was very successful. The students were able to perform some lab activities. If they don't have to connect anything to the microcontroller, they can use like a development board with built-in sensors, and they can just access through the computer, write the code, and execute the program and see through the camera what is the output in the screen. Or receive serial communication data in the computer. So I have the serial communication UART in this side. I have the code of the student and the view of the microcontroller here. So they had the three components they needed for that specific lab. Recently, we are working with Arduino with some aerospace and mechanical engineers. What happened with aerospace and mechanical engineers is that they don't have to learn in detail all the concepts about electrical engineering, but they need to know about applications because they are going to be in an aircraft or designing a system, and they need to integrate sensors and actuators. So they don't get the depth of knowledge that an electrical engineer has, but they need to be capable of implementing solutions. So we use microcontrollers, more high-level microcontrollers like Arduinos, and they can program the Arduino and send the code, paste the code, the Arduino project in that text box, and that code goes to the server and executes the program in the lab based on Arduino. For that, we use Arduino CLI. Arduino CLI or CLI is what Arduino IDE or the software uses to generate the compile, execute, all the commands that you run through the graphic user interface. But in this case, through the terminal, right? So this is a distance sensors and a linear actuator. So this system measures in centimeters how far this element is from the sensor. So they have to activate the actuator left and right, and the sensor, they need to measure with the sensor the distance. This is an ultrasonic sensor or an acoustic sensor. So that's it. So those were some experiments and some things for you to know about this topic. We know the potential. I think in general what we see here is a lot of potential to how the new technologies can be integrated. 10 years ago, we don't have IoT concept and protocols, so we were doing everything with HTTP requests and was very slow. Now we have IoT protocols and it's much more efficient. We have better streaming services and protocols. So technology is improving at a pace that we have to catch up with that and try to implement our solutions based on those new technologies. So thank you so much for your time. And I think we are all tired, me too. Thank you to the users online, the people in the IEEE Day seeing us through the streaming. Thank you so much. Thank you, Dr. Petrie.
So help me thank Dr. Zapata Rivera. Karina, can you take a picture? This is an acknowledgement for his keynote at IEEE DEMOcon. Wait. A fan club. Thank you. Thank you. There's only one piece of chocolate here left, but we can auction it. So thank you for coming to Florida Atlantic University. I wish you Godspeed and safety back home. I hope you've had a very good time here. I've learned a lot, and I look forward to seeing you in Timisoara. Thank you very much. Pardon? Oh, she left. Oh, okay. Well, just a minute. So you can sit down, sit down. We have a little something to show you as a preview to IEEE DEMOcon 2026, which will be held together with
So,
EMOOCs.
yeah, so we are getting closer to the closing session now. So if you bear with us, as we already have done the award thing, the only thing which, please allow me again to congratulate and to thank first to Maria Petri and her amazing team from here. And can you come here in front? And can we have also, where is you and where is the other guy? Come. Yeah. Karina, can you do a photo, please, with them? I really want to be able to, they have a special box of chocolate only by themselves. Where are the organizers, if you have them?
Okay, Rosie's.
Rosie, come here, Kerr. And you?
And Jose Daniel, he's
How come?
always.
Yeah, somewhere. So, and also Coral, so also Coral Wheeler, who was our administrative assistance and support. So this is the team, come. And this is your chocolate box, only for you. Thank you very, very much to all of you for organizing and for welcoming us in Boca Raton and in the Florida Atlantic University. It's been really great and we really like it very, very much. Coral, go there. No, you do only one. They said the Florida team. Karina, you will need to send a lot of photos now. Okay, thank you very much. Now we are moving to the 2026 thing. And please let me introduce Professor Radu Vasiu, who is going to be taking the baton from Maria as the next year general chair. And the conference, as you've already seen, and please again take the bookmarks. They're there. I don't have everyone with me. They are there, so take as many as you want with you, not only one, and share it in your department, in your university, and anywhere else. It's 24 to 27 of June 2026 in Timișoara, and this is the theme. So digital education ecosystems, harnessing MOOCs, AI, and micro-credentials. So this is, as you can see, from next year, unfortunately, Carlos left exactly now. This is what we were discussing there in the back is the plans for 2026, because as we are late, his plane is leaving, so he needed to go. From the first time, from next year, EMOOCs, the European MOOC Stakeholder Summit, will be joining forces with IEEE DEMOcon, and it will keep the name of IEEE DEMOcon, so digital education with MOOCs. This is how it's going to be in the future. And hopefully from 2027, we'll have even better news soon to announce to all of you. This is where is Timișoara. So it's really in somewhere in Europe, but it's, as you see in the, that's Romania. We are really at the western corner of Romania. So it's very close to Hungary and to Serbia. And we are part of Transylvania. So, which is probably sometimes even more well known. So the university is the Polytechnic University of Timișoara, as I already presented at the beginning. We do all types of education and so on. We've been established 1920. We have a lot of international recognition in international and a lot of projects and so on. And this is the department which we are going to organize more or less the conference with you. And this is the video, so this is the most important bit. Do we have also sound here? No. No. I need to stop sharing. and optimize it for video. Hold on, I'll go from the beginning. And let me just make this tiny bit. This mouse is not, only the mouse is working here. So the entire conference, Timișoara is an old Baroque city. It's overnamed Little Vienna because it was part of the Habsburgic Empire and the test bed of all the innovations. It's the first city which has electric lights in Europe on the streets, the first city with a tram in Europe. Again, the first city which has gas and canalization in Europe. I know, because it was a test bed for the entire empires to test everything, because that's when you have a city structure like this and you're coming from quite a wealthy region, it happens. So it's a very industrial city, but still full of culture. Let me try to move to the next slide. Okay, everything will be in one place in the conference center, which is exactly in the city center, so very near by the river and so on. And this is the main theme, which is going to be. The abstract submissions will be very soon, 7th of January, the latest. And then the full paper submissions after the notification at the end of January. It's going to be 15th of March, notification 15th of April. Other submissions probably around 1st of April. This is a date which is still open. And then you will have the author registration and everything by 15th of May. So to be ready for the conference in June. The website will be soon up, hopefully in 2-3 weeks maximum. The gala dinner is planned to be, this Rekaj vineyard was just elected, named again for the second row, the best European vineyard in the medium size. So it's quite well known, and it's in the city, and it's very nice, and it's going to be hopefully very good. And please join us, submit papers. We are going to, as we are joining EMOOCs, we will have also research, experience, industry. We try to attract as many as possible also from the industry. So if you do, and it's not only MOOCs, again, DEMOcon for 1 year, this is the second year, we move more towards digital education and all of the other points. So please encourage also your colleagues to come to submit papers and so on. Looking forward to welcome you. Radu?
Yes, I think I cannot say very much, just that you are welcome in Timișoara. The standards are quite high, so we will try to do our best. And we are waiting for you there. So welcome in Timișoara next year. Thank you.
And I think with this, Maria, we can declare DEMOcon 2025 closed. Thank you very much to all for coming. I know these are the last Mohicans, as we call it, staying around and still holding lines. but we'll probably meet again, hopefully next year, and enjoy the evening and have a lovely time here in Florida.
Thank you. And with that, we close the conference. And any questions that you might have on where to go or how to get there or what to do, we're here. There are maps that show you dinner so you can network and continue going. So anything you would like to ask, we're going to be around here. And we're very much looking forward to seeing you in Timisoara.
Thank you.